All right, welcome. Today we are diving into one of the greatest detective stories in all of science, the incredible journey to crack the code of the atom and figure out what the universe is actually made of. It's one of those questions that sounds super simple, right? But for literally millennia, this question has pushed some of the greatest minds in history, from philosophers just thinking about the world to the physicists who completely rewrote the rules of reality. It all started here. So, where does this all start? Well, believe it or not, our story doesn't begin in some high tech lab. It starts with a powerful idea, a philosophical concept from ancient Greece that would basically just sit there for centuries before exploding into the world of science. And I'm not kidding when I say it just sat there. Around 400 BC, the Greek philosopher Democritus came up with this idea of the atomos, this tiny, indivisible particle. But then, nothing. For over 2,000 years, the atom was just an idea people talked about. It wasn't until 1808 that a man named John Dalton finally took that idea and turned it into a real science. So Dalton comes along, and this is huge. He gives us the very first scientific atomic theory. His billiard ball model was so powerful because it wasn't just a guess. It was based on actual experiments on seeing how chemicals combine. The idea that all matter is made of these tiny solid spheres and that atoms of one element are all identical, this finally gave chemistry a solid foundation to build on. Okay, so Dalton's model was a massive step forward, no doubt, but it was all built on that one core idea, that the atom was unbreakable. But what if it wasn't? What if that tiny little billiard ball actually had pieces inside it? Well, that big question got a huge answer in 1897. That's when J.J. Thomson discovered a particle 1,000 times lighter than even the smallest atom. He called it the electron. This tiny, negatively charged particle was the first hard proof that the atom wasn't the bottom floor. It had parts. The billiard ball was about to get cracked wide open. So this discovery just completely blew up the old model. We had to have a major upgrade. We went from Dalton's simple, solid billiard ball to what Thomson called the plum pudding model. Just picture this sort of diffuse, positively charged blob, that's the pudding, and stuck inside are these tiny negative electrons like raisins or plums. This was the very first model that even suggested atoms had internal parts. All right, so we've got a new model on the table. But in science, you can't just propose an idea, right? You gotta test it. And the test for this one led to one of the most famous and, honestly, game-changing experiments in the entire history of physics. So here's what happened. A guy named Ernest Rutherford, who actually used to be one of Thomson's students, set up this experiment. He took a stream of tiny positive particles, alpha particles, and shot them at a ridiculously thin sheet of gold foil. Now, according to the plum pudding model, these particles should have just zipped right through, maybe getting nudged a tiny bit, kind of like a bullet going through tissue paper. But that is not what happened. Not even close. Yeah, most of the particles went straight through, but some of them were deflected at huge angles. And a few, a very tiny few, bounced almost straight back. Rutherford himself said it was as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. And this one shocking result completely changed the game. It forced this absolutely radical shift in thinking. Rutherford realized the only way this could happen is if all the positive charge in an atom was crammed into a tiny, super dense core he called the nucleus. And the electrons? They were orbiting that nucleus, meaning the atom was mostly just empty space. Okay, so we've solved one problem, but now there's a massive new one, a huge puzzle. According to all the physics they knew at the time, a negative electron orbiting a positive nucleus should be giving off energy, right? And that would cause it to lose speed and spiral right into the nucleus, and the whole atom would collapse in a split second. But obviously, atoms don't do that. They're stable. Classical physics had no idea why. To figure out why atoms don't just collapse, science needed a whole new rulebook. A totally bizarre, counterintuitive rulebook for how the universe works at the tiniest scales. It was time for the quantum revolution. And that revolution really kicks off with an idea from a physicist named Max Planck. He proposed that energy isn't some smooth, continuous thing. He said it can only be gained or lost in these little discrete packets, these minimum-sized chunks, which he called quanta. It's like you can't just walk up a smooth ramp. You have to climb a staircase, one distinct step at a time. So this idea that energy comes in little packets, that was the key.
Then Albert Einstein came along and showed that light itself does this. It acts like it's made of particles called photons. So, building on the work of both of these giants, a Danish physicist named Niels Bohr took these quantum ideas and applied them directly to the atom.
What Bohr suggested was kind of brilliant. He said, look, maybe electrons can't orbit wherever they want. Maybe they're stuck in specific energy levels or orbits, and they can't exist in between. They could jump from one orbit to another by absorbing or spitting out a quantum of energy, but that's it. This model worked perfectly for explaining hydrogen, but it completely fell apart for every other element. Plus, it still pictured electrons as little planets on fixed paths. All right, so we're getting closer, but the final leap, the one that gets us to our modern view of the atom, required letting go of something fundamental: certainty. It meant accepting that we can never, ever truly know exactly where an electron is at any moment. And this wild idea was nailed down by Werner Heisenberg in his famous uncertainty principle. It basically says it's fundamentally impossible to know both the exact position and the exact momentum of an electron at the very same time. And this wasn't because our tools weren't good enough. Heisenberg said this is a fundamental rule of the universe. It's just how things are. Okay, so if you literally can't know an electron's precise path, what can you know? Well, Erwin Schrödinger's work gave us the answer. He said we have to completely abandon the idea of orbits. Instead, he described the electron with math that gives us the probability of finding it in a certain area. This gives us the orbital, not a path, but a 3D probability cloud showing where the electron is most likely to be. Now, these probability clouds, these orbitals, they aren't just random blobs. They're actually super specific, and they're defined by a set of 4 quantum numbers. Each number tells you something different: the main energy level, the shape of the orbital, like is it a sphere or a dumbbell, its orientation in space, and a property of the electron called spin. Think of it like an electron's unique address inside the atom. And here's the cool part. The electrons don't just fill up these orbitals willy-nilly. Nope. They follow a very strict set of rules. They always fill the lowest energy spots first. The Pauli exclusion principle says you can't have more than 2 electrons in any single orbital, and they have to have opposite spins. They're not just abstract rules. This is exactly why the periodic table looks the way it does. And this quote from Max Born just nails it. It perfectly sums up this whole new reality. He's the one who really cemented the idea that down at the atomic level, the universe doesn't work with the certainty we're used to. It works on the strange and fascinating laws of probability. So think about where we've been. We went from a tiny, indivisible solid sphere to a miniature solar system, and finally to this fuzzy cloud of probability. It just goes to show you that in science, the story is never really over. Every single answer just seems to open up an even deeper, more interesting question.